Picture a scientist in your mind right now. You're probably visualizing someone in a pristine white lab coat, right? Staring intensely through a microscope, surrounded by sparkling clean beakers. It is so easy to imagine that scientific discovery is this completely objective pursuit. We tend to think of it as happening in a perfect, neutral vacuum, entirely disconnected from the messy, complicated real world outside the laboratory doors. But is that actually the case? Or are there invisible strings, things like global politics, massive amounts of money, and deeply held societal values, literally pulling the scientific community in very specific directions?
Welcome to This Explainer. Today, we are going to pull back the curtain on the massive, unseen forces that actually control what gets researched, what gets funded, and maybe even more importantly, what gets completely ignored. I am so thrilled to guide you through this topic, because once you start to see how tightly woven this invisible web of science, society, and politics really is, I promise you, you are going to look at every single new technological breakthrough in a completely different way. It changes how you see the world.
So, here is our roadmap for today's explainer. We're going to cover 1. The science and society web. 2. War, conflict, and innovation. 3. Who pays for science? 4. Ethics and tech constraints. 5. Real-world applications. And finally, 6. Summary and final thoughts. Let's dive right in.
Section 1. The Science and Society Web.
Okay, first things first, let's burst the bubble of the lone genius myth. Science absolutely does not happen in isolation. Take something called science diplomacy. Now, I know that might sound like a bit of dry jargon, but it is actually a brilliant concept. Think about the era we live in, right? There are intense political divisions all over the globe. But countries that absolutely cannot agree on politics or borders can very often agree on science. Science diplomacy is the practice of nations collaborating on research to build trust and solve massive global challenges. Because math and science are universal languages, they act as a unifying, peaceful force that can completely bypass traditional political roadblocks.
To really understand how this works, think of it like a massive domino effect. Let's trace the chain reaction. The first domino is politics. Political leaders have specific priorities, and those priorities determine exactly where government money goes. That's the second domino, funding. Now, that funding literally dictates what scientists focus their research on, because labs need money to keep the lights on. And finally, those resulting breakthroughs filter down to create profound, everyday changes in our society. It's this constant, endless loop. Society's needs shape the science, and then the science turns around and completely reshapes society.
To make this super concrete, just think about the grand global challenges of our time. Things like climate change or global public health crises. No single country on Earth can solve those problems alone. They're just too big. So through science diplomacy, rival nations will actually share crucial data to create international climate agreements or manage shared medical responses or even collaborate in extreme, harsh environments like the Arctic and Antarctica. It is proof that when the stakes are high enough, humanity actually can work together through science.
Section 2. War, conflict, and innovation.
But we have to be honest here. It isn't all peaceful collaboration and holding hands. We need to address a darker truth about our history. Human conflict is very often the ultimate catalyst for technological leaps. The nuclear age is probably the most famous or infamous example of this. The frantic race to develop the atomic bomb during World War II and the intense paranoia of the Cold War that followed pushed physics and engineering to their absolute limits. But all of that innovation was done in the name of national security. The power of the atom was unlocked not primarily to power our homes, but to build weapons of mass destruction.
You see, the stakes in these scenarios are almost unimaginably high. Defenders of a strong national security apparatus often point to a really chilling reality. They talk about the very real fear of an act of terror causing the immediate death of 300,000 people and the loss of thousands of square miles of livable land. When a society faces that profound level of existential dread, innovating defensive and offensive technologies doesn't just become important. It becomes absolute priority number one. Nothing else matters if you can't survive.
And as you'll see, this pressure to innovate for survival constantly evolves. In the 20th century, the focus was all about the nuclear age. But then, after the year 2001, the global focus shifted heavily toward counterterrorism technologies. And today, well, the theater of war has expanded into entirely invisible battlefields. National security now relies incredibly heavily on dominating cyberspace and even outer space. Science is constantly being drafted by the military to secure these brand new, invisible frontiers.
Section 3. Who pays for science?
Okay, let's talk about the most pragmatic piece of this whole puzzle: money. Researching the cosmos or developing advanced cyber defenses requires massive, massive amounts of capital. And here is the golden rule: whoever holds the purse strings holds the power. Generally, we have two main streams of funding. First is public funding, which typically comes from governments and taxes, usually aiming to solve grand societal challenges like public health or infrastructure. On the flip side, we have corporate funding. Now, while corporate science builds amazing, everyday products, its ultimate driver is usually profit and securing a market monopoly. When science gets heavily integrated into a business model, the research can sometimes become biased toward whatever makes the most money, rather than what is objectively best for humanity.
And this reality about funding creates a very uncomfortable truth when we look at global influence. Wealthy Western nations, specifically the United States and countries in Europe, absolutely dominate the funding and the production of scientific knowledge. Meanwhile, the Global South is highly underrepresented in these areas. Why does that matter? Well, it means the scientific narratives being told and the solutions being developed for global problems are predominantly shaped by Western resources and Western perspectives. The voices and needs of half the globe are often left out of the laboratory simply because they don't have the funding.
Section 4. Ethics and Tech Constraints.
So since science is so heavily driven by money, military needs, and political agendas, society desperately needs guardrails to make sure new tech actually helps us rather than harms us. Before we talk about those guardrails, let's dispel 3 huge myths. Myth number 1, the idea that science is completely value-free. It's not. Human bias always touches research. Myth number 2, the idea that ethical reviews are just annoying bureaucratic roadblocks. They aren't. They're safety nets. And myth number 3, the really dangerous notion that scientists have zero responsibility for how their discoveries are actually used in the real world. Ethics shouldn't be reactive. We shouldn't wait for a disaster to happen. Ethics must be proactive.
And this brings us to a massively important concept in the scientific world: the precautionary principle. I want you to think of this as the ultimate look-before-you-leap rule. It is the formal practice of intentionally pausing to deeply study the long-term ecological and social risks of a new technology before it is ever rolled out to the general public. It's a commitment that prioritizes human safety and ethical legitimacy over a frantic rush to be the first one to the market.
So what does that responsible rollout actually look like? Well, it generally follows 3 rigorous steps. Step 1, confirm efficacy. Basically, does the technology actually do what it claims to do? Does it work? Step 2, assess risks. What are the potential negative side effects on the human body, on social systems, or on the environment? And step 3, determine ethical legitimacy. This is a big one. Even if it works perfectly, and even if it's physically safe, is it the right thing to do for society? If a new discovery cannot pass all 3 of these steps, the precautionary principle clearly states that it should not be released.
Section 5. Real-world applications. Let's anchor all these massive concepts in reality for a second and look at the tangible tools this complex web of science has actually produced. The sheer scale of our capabilities right now is literally breathtaking. On one hand, engineering allows us to investigate the absolute vastness of the cosmos, launching incredible tools like the Hubble Space Telescope millions of miles into the dark. But at the exact same time, in the other direction, we can study nanoparticles. We're actively manipulating the very building blocks of life and atoms to create revolutionary new medicines and hyper-fast computing. Science today operates at the absolute macro and micro extremes of existence.
But as the saying goes, with great capability comes the potential for great corruption. Take the infamous stem cell fabrication scandal involving the researcher Huang Woo-suk. Our sources highlight this as a gripping, textbook cautionary tale. This research team completely fabricated results, claiming they had successfully cloned human embryos. And why would they fake something so huge? Well, likely the quest for international fame, national prestige, and of course, massive, massive amounts of funding. It is a perfect, terrifying example of what happens when money and ego completely override the scientific ethos, those core values of honesty, transparency, and impartiality that scientists are fundamentally supposed to uphold.
Section 6. Summary and final thoughts.
Wow, we have covered a lot of ground today. Let's do a quick recap of what you should take away from this explainer. First, remember that the laboratory is absolutely not an isolated bubble. Global politics actively shape what gets researched. Second, the terrifying threat of war and conflict has historically been a major, if uncomfortable, accelerator for human innovation. Third, because modern science is incredibly expensive, those who provide the funding essentially get to dictate the future of human knowledge. And finally, because of all these immense pressures from money and power, proactive ethics are absolutely vital to keep our society safe from our own inventions.
Which leaves us with this final, really important thought.
Science doesn't just happen to us. It isn't a force of nature like gravity or the weather. Science is a direct reflection of the society we choose to build. As citizens, the political policies we vote for, the causes we choose to fund, and the ethical standards we demand from our leaders directly influence what happens inside the laboratory. So I want to leave you with this. How will your own values help shape the scientific discoveries of tomorrow? Thank you so much for exploring this invisible web of science with me. Keep asking great questions and keep learning.